Okay. Okay, I have start recording. Okay. In our previous session, I have mentioned to you all what is meaning by the analysis of variance, or in the short form is the ANOVA for the single factor. Okay, so these are a few slides I have uploaded to the Spectrums or the Microsoft team where you can download it. Okay. So I also have gave you the examples of this scenario is if you want to compare the power with the different watts, what are the effects to the year of the observation or to the each range? Then these are the means for each. If you use a power 160 watts, you get the first mean and so on the second one. So we want to know that is it if I use a higher power, then they will produce for me the higher rate, okay, or the average value will higher. So as you can see, if you draw the following box and whisker diagram, then you can check it out. Their trend is keep increasing. Okay, so if they, of course they have an increasing, but is there any optimum level out of these four? Is it we need to stop at the 220? Or in fact, even though the graphical here, the 220 and 200 is no different. Okay, so this one is we want interested to investigate. We cannot just plotting the graph and then we say that using the 220 will be give you always the highest power, the highest yields. Okay, so this one is why we carry out the analysis of variance. Then in this slide, I have mentioned to you all, instead of doing pairwise comparisons, we will compare all together. This thing will be affected your type 1 errors, as I mentioned to you. If you do it separately, then you will get your power, the probability of doing the correct decision is 0.735. Whereas if you do it all together using the analysis of variance, you can maintain your probability of doing the correct decision is a 0.95. Okay. And then this is a diagram, I mean the structures of the data, how do we arrange with the notation of y double dot is stand for the total of the overall observation. And then the y bar double dot is stand for the grand mean, where the formula will give them as follows. Okay. And then I also mentioned to you that we are studying the fixed effect model. And then for the random effect model, later I will discuss with you. So what is meaning by fixed effect model? It means that your conclusion only can make for the levels you selected. If you selected only the level A until level 1 until the level A, then your conclusion only can make to this set of the levels. Other than that, you cannot make any conclusion. So this one is called the fixed effect model. We have another one is called the random effect model. I will discuss with you later. Okay. So our objective carry out the analysis of variance is one to compare the means from the different groups or different levels. So how are we going to carry out the analysis of variance? I have shown you. These are the formula to derive it out. Okay. They actually is based on the sum or square for the variability. So they use the observation minus the overall mean. They try to partition it to the three components. Okay, the first component will be here, the second component, and the three component because you do the expansion of square. However, this component will equal to 0. I also have mentioned to you here, so that you will have only two components. So the overall sum of square will be contribute to the sum of square for treatment and the sum of square for error. Okay, so this one is what I have mentioned to you. Okay, so our hypothesis testing is testing that the mean for the 1 equal to mean for the 2 until the mean for the A. You have a A treatment mean, so therefore we compare for the A level, the A means. Okay, whereas the H alternative will be at least one pair of the mean is different. So you do not know whether it's 1 and 2 or 1 and 3 or 1 and 4 and so on. So I have added one more slide. It's about the tau here, because later on when I go through the factorial analysis, I will introduce this one. So this one is what you have seen it before. The mean I will equal to the overall mean plus the tau I. Why I say seen it before, you can refer back your page. This one is this one. Okay, we represent the mu plus the tau I is equal to the mu I. Okay, so I have a mu plus a tau I. So the tau I is stand for the effect of them. Okay, so if you observe it, if all the mean are equal, you sum out all the mu I divided by the A, because you have a A level of the mean, they will equal to the overall mean. So from here, we can get the summation tau I will be equal to 0. So the tau I is stand for the effect from the each treatment. Okay. So from here, instead of you are writing here, all the mean are equal. Okay, our null hypothesis will say that mean 1 equal to mean 2 until the mean A. Or you also can be written as this form, where the tau 1 plus the tau 2 until the tau A will equal to 0. If you can see, if all the tau will equal to 0, means that the tau I will equal to 0. So always the mu I will equal to the overall mean. So therefore, they all have a common mean. Okay, so this we can write in this one, or our hypothesis alternative, we will say that the tau I is not equal to 0 for at least one of the I. So when you want to write your hypothesis statements, you can be write in this form, or you can write in this form. They are the same meaning. Okay, so if you write in the tau I, they must be equal to 0, because this part is 0, so every of the mean I will have a common mean. Okay, the H1 is at least one of them is not equal to 0. You do not know which one, but at least one of them is not equal to 0, then you reject the null hypothesis. Okay, this one is added here. So in the analysis of variance, they actually will relate to the what is the distribution, so that they can be compared with the critical value. So we know that if you get the sum of square, you divided by their degree of freedom, we call as a mean square. Okay, the sum of square divided by degree of freedom A minus 1, and then the sum of square for error divided by their degree of freedom. Okay, so this one is called the mean square and the mean square here. Okay, so if the treatment means are equal, means that theoretically the mean square of the treatments and the mean square for error, they were equal. Okay, if they differ, means that they will have a larger where the mean treatment mean square will be larger than the error mean square. Okay. So I have shown you to you also, this is an analysis of variance table where you have calculated the sum of square for treatment, sum of square for total. Then from here, you can use the sum of square for error is equal to the sum of square for total minus away the sum of square for treatment. Okay. So this is an ANOVA table you have. Finally, you get the F statistic here. Okay. So the F statistic is get from the MS for the treatment divided by MS for the error. Okay. So how we want to know that this thing is belong to the F? So this one, for those of you not in the statistic background, then you need to recall back what is the F distribution. F distribution is given by the chi-square distribution for the first chi-square degree of chi-square distribution divided by their degree of freedom. Then after that, you take the ratio is a second chi-square distribution divided by degree of freedom. So in fact, you can see that your SS for the treatment divided by degree of freedom is actually one of the chi-square here. And then the second one, you get the SS for the E divided by degree of freedom, you get the MSE, you get the second one. So therefore, these two, you take the ratio of these two will follow the F distribution. Okay, so the F distribution, they depends on two parameters. One of them is the first degree of freedom. So the first degree of freedom will refer to here. The second degree of freedom will refer to this one. Because why we get from here? Because the formula is get from this formula, the MS treatment over MSE. So the MS treatment degree of freedom is A minus 1. And so on, the second one is M minus A. Okay. So to calculate manually about the sum of square for total, sum of square for treatment, and the sum of square for error, then you can be simplified the formula in the following form. So this one, you can see that this part is a common for the sum of square for total and sum of square for treatment. Okay, finally, we can calculate sum of square for error. Okay, so I give you one of the example is this one. Okay, just now we have this example. So in this example, of course, we observe that the average value is keep increasing. But even though we know that it's keep increasing, but we will ask a question. Is it in the statistic sense, is it any difference in between the 160 and 180? Because the value is not different very much from the 51 to 87. Then this one is a 87 to 25, 625. Then after that, from the 625 to 707, this one is have a huge difference. But about this thing, okay, what I mean is the huge difference as compared to here is just a small difference. It's around 26 unit. So is it there is a significant difference or not? Okay, we cannot just stop at this level and then you make the conclusion. So this one is the reason why you learn the hypothesis testing to carry out the test to test whether it's significant different or no. So this one is I mentioned to you under the H0 we will write the mean one equal until the mean 4, and then H1 we write at least one pair of them is different. Okay, so based on the ANOVA table here, okay, you can get the p-value out. Okay, or if you don't want the p-value, then you can compare the f value with the f from the table, statistical table. Okay, so basically if you using any software, they will give you the p-value. So the p-value here is less than 0.01. It's referred to this p-value, the value is very small. So we compare the p-value with the alpha. Alpha is a type 1 error in your hypothesis testing. You want to carry out for the following test. Okay, so this result is all you get from the sample. May not be perfect. Okay, so therefore you need to, when you want to carry out the hypothesis test, you always set certain level of the errors where you can be acceptable. Okay, so in this case we will set the error is a 5%. Means that the accuracy of I'm doing the correct decision is a 95%. Another 5% is made due to the error. Okay, so we need to set the alpha. Therefore, we compare with the p-value. So here I set down the criteria here. This criteria actually you can find it from any of the statistical books. If the p-value is greater than alpha, then you do not reject the H0. If the p-value is less than alpha, then you reject the null hypothesis. Okay, so in this case, your p-value is less than 0.01, the values. So definitely they were less than 0.05. So therefore, we have to reject the null hypothesis. So if you reject the null hypothesis, it means that at least one pair of the mean is different. Maybe the 160 and 180, or 160 with the 200, or 160 with the 220, and so on. Altogether, you have 6 pair of them. Okay, you compare the pairwise. There is a one pair, or at least one pair is you have a different. Okay. So this one is in the ANOVA table. It gives you in general, means that you can suggest it that using the different RF power will produce the different results. Okay. So this one is I using the R codes to present the results of the mean for each one. Okay, all these means value, if you calculate manually, then this one is the results. If you can use a software, then these are the results here with their standard deviation for each power levels. Okay, so here I use it in the R codes. So this one is just now I mentioned to you the F distribution. They will follow a F distribution. Then you refer to the critical value. Then you compare with your test statistic. Okay, your calculated value is 66.8. Okay, 66.8. What you calculated is here. Then you compare with if the 5% and the 1% of the alpha. This one is referred to the alpha. 0.05. Another one is alpha 0.01. This one alpha you can set it. Then you can see that the critical value here, you calculate the F value is fall inside here. So fall inside here, it means that they fall in the rejection region. So therefore you reject the null hypothesis at 1% or at 5% as well. Okay. Then I mentioned to you that in fact this course is we do not require you to do the programming. Okay. In fact, you can be use user-friendly software like the Minitab or SPSS. You can be put in the key in the data. They can generate for you all the ANOVA table. But unfortunately, we don't have the Minitab here. Okay, so therefore I use R to do the calculation. But sometimes there is a limitation on R. R is you need to do the program. So that unless you want to write the general program to do the calculation for given the formula, you write the general formula for calculation of all the sum or square. But in this course, I do not ask you to write the program. Okay. So some of the codes I can give it to you because all these things is written because R software, they have many people writing the codes. So therefore you can use the other people write the codes and then you apply it. Okay. So this is a result of the ANOVA table. If you do it manually, so this one is here. Okay, so you can see that if the exact value of P value is 2.8 times 10 power minus 9. But in the text one, they just show you that the P value is less than 0.01. They don't give you the exact value. But here they give you the values where it's here. So obviously this P value, this one if you understand that this thing is referred to the P value. Okay, this one is referred to the P value. Most of the statistical software, they will use this type of notation or they use other notation because different software, they use a different notation. But this one, we understood that is a P value. So the P value is here. If you compare with the alpha 0.05 or 0.01, definitely your P value is smaller than alpha. So this one is lead you to the P value is smaller than alpha. So you will get the reject the null hypothesis. Okay. So here I will say that reject the null hypothesis if the P value, okay, if the P value will be less than the alpha. So you reject the null hypothesis. If you fail to reject the null hypothesis, if the P value greater than alpha. Okay, so these two, I believe that if you go through any statistical course, they carry out the hypothesis testing, then this rule will apply for all. Okay. And then after I produce for you the ANOVA, then I will tell you about in the ANOVA or in any of the statistical model, you have an assumption, the assumption for the model. So what is the assumption for model? This one is a one-way ANOVA. I mean the ANOVA with the single factor. This is a model you have. The Yij is an observation. This one is an overall mean. This one is a treatment effect. This one is an error. So the assumption is error will we say that is follow the normal distribution. The error term will follow the normal distribution with the zero mean and the sigma square. This is a true model you have. But we definitely do not know all the error from the true model because our data is not the overall data. Our data is from the sample. So therefore, this quantity of the epsilon ij, definitely you do not know. So what we can do, calculate the epsilon ij is from the sample. So how are we going to calculate this thing? Because we assume that they have a mean zero and a sigma square. So the first thing is we need to calculate the fitted equation. Fitted equation means that you have a fitted head and the mu head and the tau I head, where the error is null. Yeah. So this thing is the true. This one is a fitted equation. So under the fitted equation, I have mentioned to you, under the fitted equation, after that you can calculate a residue. Residue is equal to the observation minus the fitted equation. Okay, then you can get the residue. So the residue will be get from your sample. So therefore, the fitted equation is a mu hat plus a tau I hat. So the mu hat will equal to the mean. You use the overall y bar double dot to estimate for overall mean. But how to get this formula, I do not discuss here. This formula, you can be, if you know the maximum likelihood estimation, you know the least square estimation, then you can derive it out. Or you have a textbook, you can see how they derive it out. Okay. Similarly, for the tau I also, you can be use the mean for the I dot minus the overall mean. Okay. So finally, you will get your residue will equal to Yij minus by I dot. Okay. So this one is a residue formula under this model. Different model have a different residue. So as I mentioned, this thing is unknown. But when you want to model your the data using this model, you assume that the epsilon ij will follow a normal distribution with mean zero and epsilon sigma square. But we need to go to model checking whether this assumption is valid or not. So therefore, we calculate the residue. So the residue also must be possess the similar characteristic where they have a mean zero, the normal with the mean zero and the variance sigma square. Okay, so therefore we calculate the residue. So after we calculate the residue for all the data, these are the residue of here. I have shown it to you. The first point is using the first yi11 minus the mean for the 1 dot, because we have derived the formula of the residue. It's a I dot. So therefore, I can calculate the first value is 23.8. And the y12 is given by the negative 9.2 and so on. So you can be check the residue of here. So once you get your residue, then we can be do the normal probability plot. So this the first one is an assumption on the normality. If the point is a fall on the straight line here, then we can say that they are follow the normal distribution. But sometimes the plot is not clear. So therefore, we need to carry out the goodness of fit test. Okay, goodness of fit test, one of them may be they call as a KS test or Komogov-Sino test. Okay, or they still have other of the goodness of fit test. Okay, or you can be plot the histogram to check the distribution of the residue. Okay, so this one is a first plot, and then this one is a second plot. You want to check whether it's a variance is constant or not, because in your assumption, you have a epsilon ij will equal to mean zero, and then variance is a sigma square. So we only have a constant variance. So to check the constant variance, the second plot will be equal to the residue versus the fitted. Okay, so the residue versus the fitted equation, then if you plot for this one, residue versus the fitted equation, then if the line here or the size here is almost the same, okay, of course we cannot get the perfect. So if the shape here is almost the same, then we will say that the variance will be constant. Okay. So of course, in the checking the constant variance, you still have other statistical test. That one is called the Butler test. Okay, if you want to carry out, that one is called the the Butler test itself also is a testing whether the data is with the constant variance or not. So you can be carried out. It's called the Butler test. If you want to view it graphically, this is a graphical the plots you need to plot residue versus the fitted. Okay. Then the third one will be the independent. Is it the observation you obtain is an independent or dependent? So therefore, we will plot the residue versus the run order. So how I get the run order is just now here. The number 13, 14, 8, 5, and 4 is called the run order. So the run order means that which observation you run first. Because I think if you do the randomization, every student will get the run order. Let's say I have here in this example, I have a 4 times 5, I have 20 observation. So I want to run which one will come first? Some student maybe get the second observation is run first, then followed by the observation number 19 is run the second, and so on. Another student, you may get the third observation will run first. So the order is first. So therefore, when you do the randomization, everybody will get the different random order. So this example is just one of them only. The random order will be 13, 14, 8, 5, 4, 18, 9, 6, 16, 17, and so on. Okay, so you may not be get back the same number of the random order. Okay. So the random order, if you plot it, if they do not have any order at here, so we consider as independent. Okay, so this one is a 3 plot to checking the model adequacy. Okay, about checking your model adequacy of here. Then we only can say that our result of the ANOVA can be accepted. If you do not check the model adequacy, then you may use a wrong model, because you have assumed that this is a model you want to run for the analysis of variance in this case. Okay, so this one is for the single factor model. So if I'm not mistaken, I will stop until here during the our previous lecture class. Okay, so this one is a result from the Minitab. If you use, you have a Minitab software, then you can key in the data, you click it, they will come out all the plots together for you all. Okay, so you can check it out directly. Okay. So just now, I mentioned that if you have a problem with your assumption, if they do not fulfill for the certain assumption, okay, if the certain assumption in the, let's say the constant variance is not fulfilled, or the normality is not fulfilled. So what you can do to perform the analysis is you need to deal with some transformation. Okay, so I do not go through in detail about the transformation, because the data you need to do the transformation and then you run the analysis of variance. After that, you get their residue and then you check whether they fulfill the condition or not. If they fulfill the condition, then you can accept the results of that. Okay. So if you know, then you use other transformation. So the transformation can be the many types of the transformation. Okay. So here is some suggestion of the transformation only. But if you have the software, some software will give you the certain transformation in their software. I think it's called the box and Cox transformation. They try to transform your data to the normal. Okay, then after that you can run your results. So this one is a transformation. I just show it to you only. I do not go through in detail about it. Okay. So this is an example where you can do it manually calculation. The data they obtain from the ACI material journals. These are the data set. So they are comparing the 4 different levels for the compressive strength of them. Okay, so this one is they want to compare these 4 levels, whether there is any significant difference in between all these 4 or not. Okay, so these 2 is 2 examples where I say that I get from the I think the textbook about these 2 examples. Okay, so you can if you want to practice, you can go ahead with the here. Okay. So I continue with our story with the previous example. Just now our result is show that there is a significant difference. Means that just now we have a mean for the 1, maybe not equal to mean for the 2. We have a mean for the 2, 1. One, two, two, three, 2, 4. Oh, sorry, this one is 2, 4. Then we have a 3, 4. So these are all the 6 different combinations. Because our answer is say that reject H0, but we do not know which one is a reject cause it reject the H0. Okay, So we can have a mean 1 not equal to mean 2, or 1 not equal to 3, 1 not equal to 4, or 2, 3, 2, 4, and the 3, 4. So we do not know which one exactly. Okay, based on the just now, we have the ANOVA, the analysis of variance result. Okay, we only will know that our answer is a reject the null hypothesis. Because the p-value is a small, we reject the null hypothesis. It means that at least one pair of the mean is not equal. But we do not know which combination of them. So therefore, we need to carry out some tests. It's called the post-ANOVA comparison of the mean. Okay, so there are many of the tests to test for the comparison. So I just concentrate on the one of them. Okay, or two of here is two of them here. The analysis of variance is test the equality of the treatment means. Assume the residual analysis is satisfactory, like just now we have checking. So if the null hypothesis is rejected, we don't know which specific mean are different. So therefore, we need to determine which specific mean differ following an ANOVA is called multiple comparison problem. Okay, so there are a lot of ways to do that. Of course, they have a lot of the tests to do that. So among them are the Tukey test or the Fisher LSD different. So not necessarily all the software have all these things. Some software maybe only have a Tukey test. Some software maybe have both of them. Or they can have more than that. If I'm not mistaken, SPSS, they have many of the tests. So you not necessarily need to use all. Okay. So we need to carry out this test to check which one is different, or maybe 2 is different, or the 3 is different, and so on. Okay. So the test comparison is like this one. They were testing this one, the first mean is equal to the second mean. The mean for the second one is not equal to the mean for the first one is not equal to the second one, or I use the I and J here. Okay, so the Tukey, if you're using the Tukey technique, the Tukey technique will be compare the mean for the maximum minus the mean for the minimum divided by the standard error of them. It's a square root of the MSE divided by N. Okay, so they call as a Q standardized range statistic. Okay, the range is because they use a maximum minus a minimum. Okay, so after that, they construct the confidence interval for the difference. So the difference will be equal to the difference from the sample minus away the critical value multiplied by the standard error. For this part is a negative, and then for this part is a plus. Because we know that the distribution is a normal, so they are symmetrical distribution. So therefore, we can be used the one is minus, one is plus as a symmetrical to calculate out the mean here. Okay, so if the sample size is not equal, of course we cannot use a common n. We will use a ni and nj, because sometimes for the first treatment you use a sample size 5. The second treatment you use a sample size 3 or another. Okay. So why we want to construct the confidence interval? Because this confidence interval will let you know, for example, your mu I is equal to the mu j. So you can be written it as a you can be written this thing is a mu I. Okay, you will write it as a mu I minus the mu j equal to 0. So under the H naught, we can be write it as a mu I minus the mu j equal to 0. Or you just say that the mean is equal, or their difference is equal to 0. So this confidence interval will help you to know whether your answer is a reject the null hypothesis or do not reject null hypothesis. So because it's under the H naught, they equal to 0. So when you construct the confidence interval, you maybe get the value is, let's say you get the answer is a negative 10 and another one is a 15. You will get this thing. So because a 0 is inside the interval, so therefore you do not reject the null hypothesis. Okay. But if let's say after your calculation of the confidence interval, you get one is negative 10, another one is negative 5. The interval range is from -10 to -10 to -5. So the 0 here is not in the interval, it's outside the interval. So therefore, there is a significant difference in between these two means. Okay, so this thing, I think you learn the statistic, you should be know. Okay, so this one is why we carry out the confidence interval. Okay, we want to test whether their 0 is in the interval or out the interval. So let us go through it, the following one. This is a result of the, if I using the R to get it, is a Tukey HSD test. Okay. So this is a formula, I mean the R codes to calculate it out. So you can see that we do the comparison of the 1, 2, 3, 4, 5, 6. 6 different power levels. Okay. So under the 6 different levels of the power, then we can do the comparison. Okay. But before we do the comparison, you can see that you use a mean for the 180 minus a mean for the 160, you get the difference is here. And then at the same time, they calculate for you the lower interval and the upper interval. So you no need to do it manually using the formula here. They will calculate the lower interval, the upper interval. Okay. So this one is they calculate the here. Okay. Then after that, you can see that if you use a 200 minus 160, then this one is what you have, the lower interval and the upper interval. Okay. So after that, they also give you the p-value here. So if you still remember, this thing is a p-value here. So the p-value here will be stated compared to the alpha. So let's say if your p-value is greater than alpha, it implies that you do not reject null hypothesis. Okay. If the here you do not reject the, what is advantage over the with the two sample t-test? Hold on, later on I will let you know. After that, you have a p-value will be less than alpha, implies that you reject null hypothesis. Okay, so from here you can observe that all the p-value, if I set it as a 5% level, the alpha I set it as a 5% level, all the thing is have a significant difference. Means that the 180 and the 160, there is a significant difference. 200 with the 160, 220 with 160, and so on. All of them have a difference. Okay. So some of you asking me what is the advantage of this over the two sample t-test. And in fact, it's almost the same as a two sample t-test. But in this test, they will do it together with the, you can see that it's a 95 family-wise confidence level. So they will do all the tests at the same time. If you do it separately, if you still remember, if you do it independently, the first test, the second test, the third test, then your alpha level or the probability you are doing the correct decision will be dropped. So therefore, you need to use it or for the family-wise all together. Okay. If you want to compare this thing using the ordinary last time, the formula you have learned, then that one is only for the first alpha. The second test is another alpha. The third one is alpha and so on. So this one is the same like I mentioned to you in this slide. Yeah, here. If you do it separately, then your power or your probability of gradient characteristics will drop. So, but just now the test is they test all together. So therefore, they can maintain at the 95%. So as you can observe it, the formula here or the title of here. They will mention to you that this all the 95% family-wise, they will do it all together so that they maintain at the 95%. Okay, so the result will show us that all the sample means are different. So none of them have a different. None of them have a same. Even though the 180 and 160, they also will be very close to just now. The value is very close. The difference is very small. But if you carry out the test is still significant at the 5%. You reject the null hypothesis. Okay. But if, of course, if you set your alpha equal to 1%, then this one will be the p-value larger. So in that case, there is no significance in between the 180 and 160. Okay, so depends on you. You want your test, how accurate you want your test. If you want your test at the 99%, because if the alpha is a 1%, so you will confident that your result is 95% is sure. If you allow for the 5%, then you only have a 95% confident that. Okay, so this one is how you carry out the Hugh key. Yes, it's a Bonferroni correction is another one. So as I mentioned, they have many of them. Okay, they have many of the tests. So they have plenty of the tests to carry out the multiple comparison. Bonferroni is one of them. Okay, if you check the message where your friend is showing to you. Okay, so I do not will cover all the tests. They have many tests. If I'm not mistaken, is if you use the SPSS, they have plenty of the tests. Okay. So if you want to observe the diagram here, you can be also see that this one is a different RF power. Okay, you can see that they put the dot here. They want to indicate the 0. Is there any difference? No. So this one is a first interval here. The interval here where the mean at the center. This one is a lower interval. This one is the upper interval. So you can see that none of them will pass through the value 0. So therefore, there is a significant difference. Even though 180 and 160 is quite close to the 0, but the interval does not cover the value 0. Therefore, they still have a difference in between the 160 and 180. Okay. So this one is what if you can carry out the post here, the post test. Okay, but if your ANOVA test, you show that is no significant difference, means that all the mean is no significant difference. In fact, you no need to carry out the post test. Okay, the post host test here. Okay. So this one is another technique. Okay, it's another technique. It's a Fisher least square. The least significant difference. They're using the different techniques. Okay, so this techniques is another techniques. Okay, so if you're using this technique, if you observe that this technique is similar to your two sample t-test, it's a mean 1 minus mean 2 divided by the standard error. So you can see that you compare all the pairs at the alpha for each of the individual pairwise comparison, but does not control the experiment-wise or family error rate. So this one, if you're doing this one, you only control one by one. Okay, means that you are doing the comparison for the first pair, second pair, third pair, and so on is compared in the independently. So they do not maintain that the family-wise is maintained at the 95%. Okay. So here I just show you the formula here. Okay. This result is we using the Minitab to get it out the results. Okay. So extension from the one-way ANOVA, I have some example for you all. If your normality assumption is unjustified, so you can be use another technique is called the Kruskal-Wallis test. This test is fall under the category is called non-parametric test. So under the non-parametric test, the sense in the non-parametric test is means that they do not have an assumption from the normality assumption or any of the assumption. So they use the very simple techniques to do the calculation. Okay, the technique they are using is using the rank. Later I'll show it to you. So in the one-way ANOVA, if you cannot perform using the just now the ANOVA table, then you can be use the Kruskal-Wallis test. So it's used to test the hypothesis of A treatment are identical against the alternative hypothesis of the sum of the treatment generates observation that are larger than others. So the meaning of the Kruskal-Wallis test and the previous test are the same, except they no need to care about the normality assumption. So this one is called the non-parametric test. Okay. So under the non-parametric test, what you can do for the non-parametric test is they based on the technique is just doing the ranking, the rank of the each eye treatment. Okay. So the Kuskawaris will just take care about the rank. They don't care about the data of the observation. The first thing is in the observation there, they replace it with their rank. So they alter it from the smallest to the largest. And then based on the rank here, you can calculate out what is a statistic and then compare with the p-value. Where after you get the statistic, then you get your the probability or the p-value. Then you compare with the the p-value with the alpha. So does the Kuskawaris test consider the other two assumptions? Okay, the other two assumption is independent because when you run your experiment, you already maintain that they have you randomize it. Okay, you randomize the data. So the independent normally you can be achieved. Okay, you randomize. Then the variance is constant is not necessary, but after you run the analysis, what I mean is you run your analysis here. You run your analysis, you can get the result. You can get your result of the ANOVA. You can get your ANOVA. But is it this answer is valid or not? Then we go to checking the normality assumption, the normality assumption. But as you ask me, how about the other two assumptions? One thing is let's say the constant variance. No matter how do you transform, you do the transformation. Just now I have one slide about the transformation. No matter how you do the transformation, your constant variance can be fulfilled, but your normality is still cannot. The data cannot the normal. So in that case, you can consider using the Kuskawaris test. Okay. So the Kuskawaris test is basically is only for the normality. Your constant variance, of course, you need to maintain that they have a constant variance. Okay. So this one is the Kuskawaris test. So under the Kuskawaris test, the formula was given by here. Then of course they compare with the critical value from the chi-square distribution. If they greater than that, you reject the null hypothesis. If no, then you do not reject the null hypothesis. Okay. So this is a result. If you want to use a Kuskawaris test, they will just give you directly this is a result. Of course they don't do any calculation, but some of you may be interested about what is a chi-square here, 16.907. Actually, this 16.907 is calculated from this formula. Okay, using this formula calculate out, then you get here. So you can just check the p-value here. The p-value will be less than 0.05 if we set it as an alpha. Therefore, we know that the result is show us that there is a significant difference. Okay, so the result from the Kuskawaris and then from the ANOVA is consistent in this case. Sometimes you will get the contradict results on. Okay, especially the p-value is close to the border. For example, if you set your alpha 0.05, sometimes certain tests will go to the 0.045, or some of them will go to 0.051. So you have an inconsistent result. But what I can say, the ANOVA test, if you can use the ANOVA test, that one will be better because the test itself is more powerful. Okay, powerful in the sense that they check the power of the test. However, for the non-parametric test, because they only based on the ranking, they ignore the value itself. After they get the rank for the data, they arrange the data from small to largest. After they get the rank, they forget about the value of the data. So you can see this one is for the rank of the RI. So therefore, they are less powerful than the ANOVA test. So so far I have gone through with you is all is about the fixed effect. So I say that the fixed effect is means that your conclusion only can make to the whatever the factor levels you test. That one is called the fixed effect model. Okay. However, we can have another one is where the factor levels are chosen at random from the large population of the potential levels. So that factors is random. So for example, just now you have an example is 160, 180, 200 and the 200. The power level is 4 levels. But if we have many of the levels, we have 160, 170, we can have 180, and so on until the 250. We have so many of the levels you consider. We randomly choose out, let's say we want to test the experiment, we only choose the randomly select is 170, then another one is 180, another one is 200, and then another one maybe 210. We randomly select 4 of them from the list of here. So this thing is the factor level will be chosen at random. So this one is called the random factor. So if you deal with the random factor, means that your conclusion can be applied for the factor level here. But just now what we have discussed just now, we only study for these 4 factors. So therefore, our conclusion only can make for these 4 factor levels. This one is called the fixed factor. So the experiment for the fixed factor and the random factor, the calculation is not very much, especially calculating the SS for the total, SS for the treatment, SS for the error. They don't have the very much different. Okay. So this thing is called the random effect model. Okay. So after we can be concentrate on the certain level of them, our conclusion we can make for the all of them. Okay. So under the random effect model is I give you this is an example of the looms. Okay. So the textile company is wish to study about this of the fabric for the large number of the looms. So they have a large number they don't mention about here, but they selected randomly at 4. Okay, so because of the levels they selected at the 4, so we know that our conclusion later on we can be apply it for the whole population. If the whole population consists of the 100 of them, so our conclusion is can be applied for the all. Okay, so you can see that if you refer to the table itself, the table itself is no different with the fixed effect model. It's the same. The value is all the presentation of the values is same. But if you refer to your scenario, then you know that this loom is selected at random. So therefore, they call as a random effect model. Okay. So under the random effect model, here are the explanation of that. The random effect, the looms are the random factors. Okay, so in this case, also we only study the single factors here with the A equal to 4 levels and the sample size is equal to 4 for each one. Okay, so your levels is here, you select only 4 levels out. So under the random effect model, the model is a bit different from the previous one. For the fixed effect, this is a model. For the random effect, this one also is a model. But if you can recall back your fixed effect model, I only have a random, here have a certain distribution. The epsilon I will follow the normal with the mean 0 and the variance sigma square. You have only this thing. But because now we are studying the random effect model, the tau I here is no longer as a constant. Because you study let's say you study a fixed effect model, the tau 1, tau 2, tau 3, tau 4, you already fixed. Therefore, they are fixed number. But now, because you selected out the looms from the list of the population, therefore, this part is become the random. So if they are random, of course, they have assumed that they follow the normal with the mean 0, and they also have their own variant. Okay, so in the random effect model, you have a 2 component of variance here. One is come from here, another one come from here. Of course, this one is a constant because it's the overall mean, then this one is a constant. Okay, so therefore I can write it out here. The variance of the both of them, you consist of the variance for the error and then variance for the tau here. Okay, so in the random effect model, the variance here is very important. The variance here. Okay. So in the fixed effect model, okay, I will compare two things. In the fixed effect model, we are testing the equality of the mean. We are testing the H naught. The mean for the 1 equal to mean for the 2 until the mean for the A. If you have an A level of mean. Or you can rewrite it as a H naught tau for the 1 equal to tau for the 2. Okay, the treatment here, the tau I will be equal to until the equal to A equal to 0. This one is just now I have mentioned to you is under the fixed effect model. So you can return as this one. But now you are no longer as a fixed anymore, so they are random. So therefore, our null hypothesis, instead of writing in the equal mean, we are writing the sigma d tau square. So the under the H naught, the sigma tau square is equal to 0. So if they equal to 0, you can another one is a sigma 1 is greater than 0. Means that there is a large variation. So the variance equal to 0 is what is meaning here. So you recall back the model here. They of course they can random from here. This one is random from the error. So if the variation of the randomness of the sigma I tau I is equal to 0, it means that they don't have the variation. So almost all of them you can treat it as a common. Okay. So therefore, under the random effect model, our null hypothesis and alternative will return in testing the variance, not testing the mean itself anymore. Because a fixed effect, we are testing each one. Okay. So under the random effect model, besides the calculation, they also have a certain parts we need to take note. But over here, over this example, I don't go through the very detail about the random effect. I just want to introduce for you. But when you go through the random effect model, they need to calculate the something is called the expected mean square. Okay, the expected mean square for the MSE is equal to sigma square. Okay. Of course, this one is not directly equal. You need to do the derivation, then you can get is equal. The expected for the mean square treatment will equal to sigma square plus the n times the sigma tau square. Okay, so these two expectations you need to write out. Of course, there is a shortcut to write out this thing. Okay. So these two variants, why we need to know the expected of here? Because this one will lead you to get your test statistic here. So your test statistic will equal to MS treatment divided by MSE. Okay, so how I say is related to here, because if you still remember, under the H naught, when you carry out the hypothesis testing, you will say that the H naught, the tau square equal to 0. The H1, your tau square, sigma tau square greater than 0. So we set your alpha. We set the alpha is equal to certain value. Okay, alpha is a type 1 error. Because what is the alpha here? Alpha definition is they call as a type 1 error or the probability of type 1 error. Also is given by the probability for you to reject H naught when H naught is true. Okay, this one is a definition for the alpha. It's a reject the H naught when the H naught is true. So when you set your alpha of the type 1 error, in fact, you have set the error is say that you reject the H naught when the H naught is true. So you always will assume that your null hypothesis is true. Okay, when you carry out any of the hypothesis testing, you will assume that your H naught is true. So if under the H naught is true, the variance for the tau square equal to 0. So this one will be checking for the here. Under the H naught is true, this part will equal to 0. Okay, this part equal to 0, so the variance for MSE will be equal to variance for the MS treatment. So therefore, our test statistic will equal to the MS treatment over MSE. Okay, so this is how do you get out your test statistic? Okay, so they will come from the expected mean square. But here, because we only study the single factor, maybe you cannot see any difference. You can see that the formula, this one, will be similar to the fixed effect model. But when you have many factors, then you can see there is a difference. Okay. So in the variance component, we also can estimate the variance, because just now we say that the expected value of MSE is equal to sigma square. So therefore, the estimated of the sigma square, you can use the MSE to estimate your sigma square. And then from the second formula, you also can estimate your sigma tau square. What is the value of here? So you know at least the variance of the error, the variance for the tau square. Okay, so this one is under the random effect model. Okay, so under the random effect model, you cannot be used ordinary ANOVA anymore. I mean in the R software. So I will use a linear model here. Then you will get your result of the random effect model. Okay. So they come out the statistic of the residue here. And then also they know that what is the variance for the first component of the variance. So the 6.958 is referred to what you have here, the variance of the tau here. The variance for the residue is 1.896 will be here, is here. Okay, so the MS treatment and MSE, the calculation of all the MS is similar to just now what you have studied in the fixed effect model. The calculation is no different. Okay, sum or square for total, sum or square for treatment, sum or square for error. The calculation is similar to the beginning of the fixed effect model. Okay. So this one is the output. If you want to run it out, all the variance component estimate. And then this one is the output if I'm using the Minitab. Okay. So if you're using the Minitab, you can see that this is the ANOVA table. Okay, the ANOVA table, but on top of them, you can see that they emphasize on the expected value here. The expected value here is looms is equal to 2 plus the 4 times 1. The error is equal to 2 here. So what is the 2 here? The 2 here is referred, if you can recall back what you have here, what is the expected value of the here. The expected for MSE is sigma square. The expected for MS treatment is sigma square plus n times the sigma square, sigma tau square here. So in the Minitab software here, they also will produce for you this one. 2 here is a stand for the variance for the MSE. Okay, so the looms also have a 2 plus the 4 times 1. So 4 here is stand for your sample size, because your sample size is a 4 multiplied by the variance from the first component. Okay, the 1 here is referred to the first component variance here. And then the 2 here is referred to the variance for the error. Okay, so you need to make sure that you understand, let's say you want to use a Minitab, this one is the output you have. Okay. So the estimated, you can see that if the estimated is 6.958 and then the 1.896 was similar if you're using the R software. You're using R software, this one is a parts of here you have. Okay. So this one is all the plots, residual plots to confirm whether the distribution is fulfilled or no, about the constant variance, normality, and then the independent. Okay. So this one should be the last one for the here. I give you the one of the example here. The keywords is if they want to testing for the chemical, their chemical is selected at random from the large population. Then we know that this chemical is come from the random effect model. Okay, if they are fixed for the certain chemical, then this one will become the fixed effect model. So if the fixed effect model, then you're comparing the means, the first mean, second mean, and so on. So when you do the analysis, you cannot just somebody is give you the data set, then you do the analysis without knowing what have they done or how they select the data. Like this thing, if they given me this table, so I thought that the chemical 1, 2, 3, 4 is already fixed. So I say I will use a fixed effect model to run the result. But in fact, this 1, 2, 3, 4 is come from the population. So therefore, they are randomly select out. Then in that case, I need to consider using the random effect model. Okay. So in here, I just introduce for you the random effect model because in our course here is not in the syllabus here. So under the random effect model, you also can have another thing is called the mixed effect model. You can have a certain level is fixed, certain level is random. So this one is called the mixed effect model. So under the mixed effect model, the analysis will be complicated. Okay, because you need to know especially the mean square error here. You need to know the mean square error. You need to know what is the expected mean square error. Then you only can get your appropriate test statistic. Okay. So I will this one is the last slide for the chapter number 3. Actually, this thing is should be the introduction. Okay. So I will upload this thing to the Spectrum. I will upload this thing to the Spectrum to let you to you just recall back. I think some of you have shared the books, have share you all the books. Then it's better you read through the contents of that. Okay, so that for those of you who are not familiar about what is the meaning by analysis of variance, or this one is the first time you hear about it, then at least you can go through it. Okay, from the single factors. Okay. If you do not have any of you have a question. Okay, I also have uploaded the chapter 3, 4 and the chapter 5 note inside there. Okay, so this one also is very important in the second section. Now I'm using another software to do it because I think this one the Microsoft Edge will be when I writing will be smoother. Okay, will be smooth than just now I using the PDF. Okay. So now, if you do not have any question, okay, if you do not have any question, I will just continue until the 7:30. Then we have a break. Okay. So in the second part here, we will do the extension of the from the one factor ANOVA. If you still remember in our previous section, in the chapter number 3, we only study is single factor. We are using the idea of the analysis of variance, decomposition it into the different components. So now in the chapter number 4 here, we will introduce for you what is meaning by the I will introduce for you what is meaning by the blocking factors. Instead of you have a single factor, but you have another thing is called the blocking factors. Okay, so what is a blocking factor? So we are using the way of the analysis is called the randomized block and the Latin square designs. Okay, so first thing you need to know what is a blocking factor. The blocking factors is called the Nelson factors. Nelson factor means that those are the factors you are not interested at all. For example, now I want to compare the student performance from the first year, second year, and the third year. Maybe you are in the first year student or the first semester student. the second semester student, the third semester student. I want to compare these three groups of the students, the performance. So when I collect the data, I will collect a few students is come from the first semester, a few students from second semester and the third semester. And then I carry out the analysis of variance or the one factor analysis variance and then do the comparison. But the problem is when I'm collecting this type of the data, they have some effect were affected. What is the effect there? For example, if the first group of the first year student, you take too many of the male student, then the result may be better. Or you take the female student, then the result will be better. So we can be say that the gender is when I want to compare the three groups, the gender itself also have some effect on your analysis. But the gender is not your the target of your study. Your target of the study is want to compare for the semester 1, semester 2, and the semester 3 student performance. But when we collect the data, this effect already come in. So that one is called the Nelson factors. So how we want to eliminate out the Nelson factor? So the techniques we are using is using the blocking. Okay, we use the blocking to remove it out the factors here. Or we want to eliminate out the sum or square component there. Then we can analyze our analysis based on the comparison of just now, the first semester, second semester, and third semester. Because our target is only study for this thing. If we recall back the previous notes, we have a RF power. We have a first power 160, 180, 200, and the 1220. This one is your main factor. But when you do the collection of the data is come from the different supplier. And then the raw material from the different supplier also will affect your results. But it's not your target because the raw material it just help me to get the analysis out. But it's not my target to compare the output from the different supplier. So I need to use a blocking technique to eliminate out these Nelson factors first before I can carry out the comparison for the different RF power. So now you are learning how to eliminate out or how to get out the blocking here. And then of course the blocking you can have Nelson factor is a single Nelson factor. You can have two Nelson factors and so on. Okay, so these two is two of the examples of how you want to do it, the Nelson factors. So the block, the design is called the randomized complete block design. So it's actually extension from the ANOVA, you plus another one more component. So you also will recall back what you have studied before. You have from the one-way ANOVA, you break the sum of square for total to the sum of square for thickness and the sum of square for error. So now our idea is just if we have an additional one more blocks, then we have another one more sum of square. Later you can see that. So other blocking scenario will be equal to the Latin square design. Latin square design is where you do the blocking for the two Nelson factors. So the blocking is a technique for dealing with the Nelson factors. So the Nelson factor is a factor that probably have some effect on the response, but it is not of not interest to the experimenter. So it's not our target. However, the variability is transmitted to the response need to minimize. In fact, there is an error there. You totally cannot say you remove it. You only can be minimize it. Okay, so the Nelson factor is you are not interested or you are not interested. Okay, your Nelson factor is not your factor you are interested on. So typically, Nelson factor include the batch of the raw material, operator, piece of the test equipment, the time, different experimental unit. So these are the some next Nelson factor. Because when you want to testing for your products, your product, some of the product maybe come from the supplier A, supplier B, supplier C. So you have a different batches of the raw material. But this thing is they can affect your result. So we use a blocking to eliminate it or try to minimize it. Or you can see this one is an operator. You cannot avoid, you can have so many operators, all of them must be give you the same results. So therefore, the operator also is one of the Nelson factor. The test equipment, because some equipments, the accuracy of equipment can be different. The time of the time also is a shift. Let's say some of the staff they doing the morning shift, afternoon shift, and the night shift. So some of them the night shift they very tired, and then the morning one they can be work very efficiently. So this one the time or the shift also affected your result, but it's not your target because this one is a nature itself. Unless you can maintain that, you don't have the Nelson factor at all. If your batch of the raw material, if all your raw material, you expect that they come from the same supplier and then no different, then you totally no need to consider the blocking at all, because you can show that you don't have this effect at all. Your operator, if all the operator will give you the same performance, so you totally no need to consider the blocking. So the blocking may not be in your analysis. If you think that you do not have a Nelson factor, you totally no need to consider the Nelson factor at all. Okay, so many industry experiments involve the blocking. Okay, failure to block is a common flaw in the designing and experiment, because this one will affect your result. Later on, when I show you the formula, you can aware that. Okay. So here is a few of the parts here. If the Nelson factor is known and then controllable, you still can control it, then we are using the blocking. The blocking we are going to learn it here. If the Nelson is a known but you are unable to control, you can use another analysis. It's called analysis of covariance. Okay. So if the Nelson factor is unknown and uncontrollable, then how you want to do it? If they are unknown and then you are unable to control. So this one is through the randomization of your observation. When you every time you take your observation to run the experiment, you need to randomize the order. Okay, you have observation number 1 under 20. You cannot say the first come will go to the first one, the second come will go to the second one, and so on. You need to do the randomization. So once you randomization, they are assigned it randomly. So in that case, you still can be minimize it. Okay. So sometimes several source of the variability can be combined in the block. Then the block become the aggregate variable. Okay. So you can do the combine. So let me introduce for you. This one is one of the example. Okay. Maybe I will need to here. I don't want to read one by one. Okay. The first one is actually they want to testing the hardness test, the hardness testing example. So they have 4 different tips produce the different hardness reading on the Rockwell hardness tester. So they have one to compare for the 4 different tips here. Okay. So they have assigned the experimental unit. Okay. So this one I do not want to read it out one by one. I just show it to you. Okay, maybe I show you the example of here. Okay, so in fact, I go through this one. Actually, they want to testing for the 4 different tips of them. The first tips and the second and so on. But because of when they collect the data, as I mentioned to you, they may come from the same raw material. So they consist of the 4 different blocks here. The first block will be here, the second block, the third block, and the 4th block. Okay, the test component is considered as a block here. So this one is what the experiment is here. Each component is called the block. They have more than it is a more homogeneous experiment on which they test the tips. Okay, so the variability between the blocks can be large. The variability within the block should be small and relative. Okay, so the block is a specific level of the Nelson factor. Okay, so when we want to do the blocking like this one, they appear the block effect there. We do the randomization, then we are doing a block represent a restriction on the randomization. So what is meaning by restriction on the randomization? Before that, you have all the observation. You have a 1 to 20 observation. You randomize at all. How do you assign it? Maybe the observation number 20 is come first, then followed by observation number 15 is come the second one, and so on. You do the randomization all because all the 20 items, they are homogeneous. But when you have a blocking there, they have another block, so we will do the randomization is within the block. So therefore, they say that the randomization restriction on the randomization. So how they do it, you can see that if you have a block number 1, you have a block number 2, you have block number 3, you have block number 4. So how you will assign it, you will do it randomized. Randomized within the block itself. They randomize within the block itself. Okay, you have 4 tips here. You want to compare for the 4 tips here, so you randomize it. Then you assign for the first observation is go to this one, tip number 3. The second observation is tip number 1, and so on. Okay, they cannot do the randomization in general, in overall. They are doing to a randomization within the block. Okay. So this diagram here, you can see that you have 2 structure here. Here is represent the blocks. The row for each row is represent the treatment level. Okay. So once again, we are interested in testing the equality of the treatment mean. Okay, we are interested. Our final answer is still testing the treatment mean. We are testing for the tips 1, tip 2, tip 3, tip 4 means. We are not testing about the test component. We are not interested about block. But because when you run the analysis, they consist of this block effect. So therefore, we need to remove it away. So, but now we have to remove the variability associated with the Nelson factor, or we call as a block. Okay. So this one is just I mentioned to you that we randomization, the randomized complete block design. It means that for each block you do the randomization. For each block you do the randomization of the observation. So therefore they call as a randomized complete block design. You have a blocking. If you do not have a blocking, you can refer to chapter 3. It's called the completely randomized design. You do not have a block, but now because you have a block, so therefore we do the randomized complete block design. Okay, we have a complete block design. We have another version, it's called incomplete block design. Okay. So they have a complete block design. It means that all the observation here will run to the treatment levels. Okay. Okay. So let me introduce for you what is the formula for the RCBD, the randomized complete block design, as compared to the ANOVA previously you have. Okay. Or we don't want to call as an ANOVA, we call as a single factor. So as you can observe it here, we have additional this part. Our model before that, we only have an overall mean. The tall I is a treatment mean. Now we have an additional one is a beta j and the epsilon ij. So this beta ij is referred to the block. Okay, we have a block effect here. Okay, so we have a block effect of here. So, but our target is, even though we have a block, but our target is still want to compare the different mean. We are not interested about the block, because when you do the analysis, you want to extract out the component of the block. We really want to compare it just this thing. Okay. So I think I will stop until here first. I let you to have a break. For those of you want to take your dinner, you just go ahead first. Okay. So can we join back at the 8 o'clock? Okay, so you just take the break first, then we come back at the 8 o'clock. If you have any message,